So let's talk about the quantities. Physical quantities in engineering have 5 things. They have a name, they have a value or a number that you can assign to them, right? They have a dimension, they have a unit, and they have 6 digits. These are the 5 things, right? So if I said my weight is, let's say, 60 kilogram, right? So weight is the physical quantity, 60 is the number, kilogram is the unit, and dimension is implicit, which is the dimension of mass, right? Well, of course, when I say weight, it's not right? I should say mass. But most of the time, we say weight. And people understand what we're trying to say. And you have the 6 digits, right? So if I say 60 kilogram, how many 6 digits I have? 2? Is it 1? Good question. It's ambiguous. So when you say simply 60, the last 0 could be significant or may not be, right? So those are the 5 things that you have. Now let's look at them. First, we'll talk about the dimension. So what is dimension? It's an abstract concept. Dimension is an abstract concept, right? And it is not attached to any unit or any scale, right? So for example, if I said that, look at the circle, the perimeter of this circle, the length of this line, height of this boy, and the diameter of this soccer ball. What's common to all of them? All those physical quantities, different from each other, have same dimension, the dimension of length. So dimensions, which is an abstract concept, are very few. There are not too many base dimensions, fundamental dimensions. So fundamental dimensions that we deal with are mass, and we write it usually as uppercase M, the length, uppercase L, time, uppercase T, current, I, and temperature, theta. There are only very few base dimensions. Rest of the physical quantities, they can have what are known as derived dimensions, which are dependent on the base dimension. So for example, area. Area has dimension of L square, L times L. Volume has L cubed. Velocity has length over time, right? L over T. And acceleration is L over T squared. So when I say analyze something from a dimension point of view, don't use units. That's very important. I've seen students making this mistake because maybe this is how you did things in your high school classes or some other classes. When I say analyze something from a dimensional point of view, use M, L, T, I, and theta as a symbol to do the analysis. Don't use kilogram or meter or pound force or feet to do the analysis, okay? Because then you are picking a unit. So these are all derived dimensions, right? But then there are quantities that are dimensionless. Mach number. What's Mach number? Anybody? What's Mach number? A multiple of the speed of sound. Anybody else? What's Mach number?
The speed of an object relative to the speed of sound.
So it's the ratio of the speed of an object moving through fluid and the speed of sound, right? So since you have the speed in both numerator and denominator, it's a dimensionless quantity. It has no dimension whatsoever. You have a ratio. What about angle? Is angle a dimensionless quantity? Yes? No? No? What's the definition of angle? What is the definition of angle? Anybody? How do you define an angle?
If two straight line meets in a certain point and create.
Anybody knows the definition of angle? Radius? Sorry? Radians? So radians are one of the units, right? So if you attach unit, does it mean that it's a dimension quantity? Well, it turns out that actually radians is not a unit. Degree is not a unit for angle. They're not units. So you may have been told that they're actually units, but they're not units. Right, so what she's saying is that maybe it has something to do with the arc length and the radius, right? I'm hearing all the right words. So angle is really nothing but the ratio of the arc length and the radius, right? That's what angle is defined as. So if I have an arc length, let's see if I can use this. If I have an arc length, right, then the angle it subtends at the center, theta, is equal to the arc length, which is S, divided by the radius, right? So if you look at this definition for the angle, which is the ratio, numerator and denominator both have the quantities which have dimension length, which means angle itself is a dimensionless quantity, right? So if you're looking at the total angle subtended by the whole circle, the perimeter is 2 pi r divided by r, so that gives you 2 pi. right? This is your high school definition of the angle, or you may have seen the definition of the arc length that can be computed from the angle and the radius. So angle is also a dimensionless quantity, and contrary to what you may have thought so far, radians and degrees are not the units, because units are something that you attach with a quantity that has dimensions, right? What about trigonometric functions? Sine of something, cosine of something. Do those quantities have any dimensions? No? Why not? Because they're ratios. So if you want to define sine of an angle is defined by, in a right angle triangle, just a simple example, if this is D, this is L, then sine of theta is D over L, right? And that's a ratio. D over L is a ratio. D has dimension of length, L is also a length, so trigonometric functions also are dimensionless quantities, right? So there are quantities that have dimensions, there are quantities that have no dimensions, and if you know their basic definition, you can find out what they are, right? Okay, units. Now units are a relative concept. Unlike dimensions, which are absolute or abstract concepts, units are relative. And there are quite a few unit systems out there. Okay, so that makes things a little bit complicated, but it also gives rise to a richer way of operating. There are two systems of units that we mostly deal with. One is the USCS system, which is the US customary system, also known as English system, although English really don't use it anymore. It's also called FPS, for foot pound second system. In this country, we mostly say USCS system. And the very popular one is SI, or International System, also known as metric or meter kilogram MKS system, right? And it has been decided that whole world should really adopt just the SI system. Unfortunately, most of the businesses in this country still use USCS system, so we have no choice but to learn both of them. Okay, you have to be proficient with both USCS system as well as SI system. If there are any international students in this class coming from maybe abroad, let's say Asia, they're probably more familiar with the SI system because that's the predominant unit system used over here. Over here, you have both of them. So you will see problems where you have things given in pound, things given in kilogram. So you have to know how to go from one to another, right? Okay, so we have talked about the base dimensions. These are the generic symbols that we use for them. And we have two unit systems. So in both SI as well as USCS system, each of these base dimensions have what are known as base units. Because they are base dimensions, so we have base units for them. For derived dimensions, you'll have derived units in each system. So in SI system, the length has meter, time has second, which is common, mass is kilogram, force is a derived unit in SI system. So we derive the unit of the force from the base units. For temperature is the Kelvin, so it's not centigrade, and you have for electric current, you have the ampere. For USCS, the difference is in the length, so this is meter, this is feet, second is common, mass is kilogram, but the unit of mass in USCS system is the derived one. On the other hand, the unit of the force in the USCS system is base. So the unit of the force in the USCS system is pound force, sometimes also written as simply as pound, LB, but more correctly speaking, it should be written as LBF or pound force. Temperature has base unit as Rankine, and electric current is same as ampere, right? So in case you're curious, the relationship between Kelvin and Rankine is given by this. So you can see 0 degree is same, right? Because 0 degree R is same as 0 degree Kelvin, okay? But the linear scale is different. So it's not same as centigrade or Fahrenheit.
Isn't the temperature is Fahrenheit in USCS system?
No. It is a derived unit. It is not. Rankine is the base unit in the USCS system. Okay. Although we do use, you're right, we use mostly Fahrenheit in this country. Yeah. We don't talk about centigrade that much. Okay. So the thing that you need to pay attention to is this part, the force. The unit of the force in the SI system is derived, but the unit of force in the USCS base system is pound force. So then the question is, well, how do we get the unit of mass in the USCS system? Well, we get the unit of mass in the same way as we get the unit of force in the SI system. So same formula, same approach that we take. Okay, so we'll talk about that. Now, how do we get the unit of mass in USCS system? How do we get the unit of force in the SI system? Comes from this formula, which is Newton's second law, right? Newton's second law says that if you are given the mass of an object, if you know the acceleration of this object, then the force applied on the object to cause that acceleration is equal to mass times acceleration, right? That's Newton's second law, F equal to ma. So if you know the force, you know the mass, you can find out what the acceleration would be. In that case, it's more like you know the cause, the push or the pull, and you can find out the acceleration. Or you can say, hey, I know I need to have this much of acceleration because I want to go this fast, right? And I know the mass, so how much force would be needed to get that acceleration? So again, you use the same formula to get that. So if I'm trying to derive the unit of force in SI system, I need to know the units of mass and acceleration, right? So let's substitute that in this formula. So the unit of the dimension of mass is m, and the acceleration is defined as rate of change of velocity, right? Rate of change of velocity. Velocity itself is rate of change of displacement. So the unit becomes, or the dimension becomes, L over t square, right? L over t square. So you can write this as ml times t to the power minus 2, right? So that's the dimension of the force expressed in terms of base dimensions, the fundamental dimensions. If I want to get, let's say, the dimension of mass, because I know the dimension of force, which is what we will have in the USCS system, then I just have to rearrange this formula, take t squared on this side, take L on this side, and I will get basically m equal to f times t squared times L to the power minus 1. Same formula, we can go from force to mass or mass to force. And we'll use these formulas to get our units in the two systems. So this is the most important slide, right, for chapter 3, really. So pay attention over here, because this is where students make a lot of mistakes. There are a few facts that you need to understand. First is, this I'm repeating it, mass is a base unit in a SI system. So kilogram is a base unit in a SI system, while force is a base unit in the USCS. Okay? So these are your starting points. USCS system has two different units for mass. One is a pound mass. One is a pound mass, and the other is slug. So there are two units for the mass in the USCS system. So then the question is, well, how do we relate slug with the pound mass? And which one should we really use in formulas, right? Those are the things that we want to know. There are two facts highlighted in red over here that you need to memorize and remember. You need to commit it to the memory. Number one fact is that 1 pound force acts on an object of mass 1 slug when it undergoes acceleration of 1 feet per second squared. Now, there is nothing new in here. You actually know most of this stuff. You know the definition of a Newton, right? What's the definition of a Newton? Definition of 1 Newton is that if you have a mass of 1 kilogram, which is accelerated at 1 meters per second squared, then the force produces 1 Newton, right? F equal to ma. M being 1 kilogram, acceleration being 1 meters per second squared, produces a force of 1 Newton. Same thing over here for the USCS, except that the force is no longer Newton, it's 1 pound force. The mass is not 1 kilogram, it's 1 slug. And the acceleration is not 1 meter per second squared, but 1 feet per second squared. Right? So all you're doing is taking that basic definition that comes from the SI system and writing your units in USCS system, where the mass is slug, acceleration is in feet per second squared, and the force is pound force. Right? So if you look at this fact, you can clearly see that 1 kilogram in SI system is equivalent to 1 slug in USCS system, right? So the role played by a kilogram in SI is the role played by slug in USCS. That's it. That's all it is. So there is a clear parallel between the two, right? And everybody should remember this, right? Kilogram, slug behave similarly across the two unit systems. Number two fact is, and this is something you need to pay attention to, is that 1 pound mass of something weighs 1 pound force. And that's just a definition. So 1 pound mass of something weighs 1 pound force. Now notice, I didn't say 1 pound mass is equal to 1 pound force. That would be wrong, because you can't equate mass with the force. What it is saying is 1 pound mass of something weighs same as 1 pound force, right? Now, when you go to buy something in the grocery store, how do you buy? Let's say you want to buy 5 pounds of apple. What do you really say? I want to buy 5 pounds of apple? What is that 5 pound? Is that pound force? Is that pound mass? What is that 5 pound? Yes? It's a unit of force. 5 pound is a unit of force. So when you simply say pound, you're essentially saying the weight of my apple should be 5 pound, right? But if you look at this fact, it's telling you that 1 pound mass weighs 1 pound force. So 5 pound, when you say, is also 5 pound mass. right? So when you buy 5 pounds of apple, it doesn't matter whether you say I want to buy 5-pound mass of apple or whether I want to buy 5-pound force of apple, because 1 pound mass weighs 1 pound force, right? Okay, so how do we translate all this into conversion formulas? So if you have heard about the conversion formulas to go from slug to pound mass and things like that, you will now see where they're coming from, right? So first thing is, let's look at the SI system. In the SI system, using the force equal to mass times acceleration definition, if you have a mass of 1 kilogram, acceleration as 1 meter per second square, then what you get is 1 kilogram meters per second square, and kilogram meter per second square is defined as Newton, right? So instead of saying kilograms meter per second square, once you multiply mass with acceleration, mass being in kilogram, acceleration being meter per second square, you get your force in Newton right away. If you have a 5 kilogram object accelerating at 2 meters per second square, you get 10 kilogram meters per second square, which is same as 10 Newton. And I'm pretty sure that none of you have any problems with this, right? Okay, good. Let's see what happens with the USCS system. Because in USCS system, the mass is a derived unit, right? Here we derived the force to be the unit. Okay, again, same definition. We already know that one slug mass accelerated at 1 feet per second square gives rise to a force of 1 pound force. So let's write that. F equal to ma, mass being in slug, acceleration feet per second square. We get mass times acceleration slug feet per second square. And this whole thing is nothing but 1 pound force. So I can write this as pound force or pound, right? So pound force, same thing. So 1 pound force is equal to 1 slug feet per second square, right? So this is coming from the first fact. Now let's use the second fact, which says 1 pound mass weighs 1 pound force. So we got that 1 slug is equal to, this is just a reiteration of that. So all I'm saying is that, well, let's take the feet per second square on the other side, and we can write slug equal to pound force times second square over feet. So that's all it is. So it's just a rewriting of this, and where I'm writing the slug on all by itself on the left-hand side. So second fact, weight of 1 pound mass is 1 pound force. What is the weight of something? Weight of something is nothing but mass times gravitational acceleration, right? So 1 pound force is now equal to the mass being 1 pound mass times g, which is gravitational acceleration in feet per second square, as 32.2 feet per second square. So when you write this, we get 1 pound force equal to pound mass times 32.2 feet per second square. And I know pound force times second square over feet is nothing but slug. So I get this as my conversion formula, which says 1 slug is equal to 32.2 pound mass. 1 slug is equal to 32.2 pound mass. So if, let's say, you were given a problem, and you will see a lot of problems like these where you'll be given maybe the weight of an object in the USCS system as, you know, I have a truck of 5,000 pounds. And I want it to accelerate at, I don't know, maybe 40 meters per second square. That's too much, but, you know, let's just make up some numbers. How much force is needed to make this truck accelerate at that acceleration? You can simply take 4,000 pound force multiplied with the acceleration given to you, because in the F equal to ma formula, the mass should be in slugs. Mass should be in slugs in that formula, which means that you need to convert your weight of the truck given to you into the slugs. So how would you get that? Well, we know that 1 pound mass weighs same as 1 pound force, so you need to divide by 32.2 to get everything in slugs. That's it. Once you have that, then you can plug it into the formula, right? So let's look at an example. So first of all, we want to buy 5 pounds of apple, right? That's an example. So what is 5 pound? 5 pound, the mass or force? Is force. 5 pound mass weighs 5 pound force. But over here, if you simply say 5 pound, technically speaking, it's the force, it's the weight. How much does it weigh? 5 pound or 5 pound force, right? What force is produced when it is accelerated by 2 feet per second square? Now this 5 pound is really the weight, which means we need to convert into the slug. How do we do that? We divide by 32.2. Because in this formula, the mass should be in slugs, right? Just as if you were using the SI system, the mass should be in kilogram. Here, this should be in slugs. Multiply the two, and you get something like this, right? So we get that. Okay, that's good. Now, we also have derived units, right? What are the derived units? Derived units are the ones that come from the base units, okay? And there are quite a few of those. So this is just a sampling of them, right? It's not like that I can present all of them over here. So in the SI system, micron or micrometer is a derived unit of length. And what is that given as? As 10 power minus 6 meters. You know that. So this is a derived unit. Liter, which is 1,000 cc or 1,000 cubic centimeters. Cubic centimeter can be written into meters, so that's 1,000 times 10 power minus 6 meter cube. So that gives you 10 power minus 3 meter cube. So that's 1 liter is a derived unit in a SI system, right? Newton is a derived unit. Newton meter is a derived unit. Pascal is also a derived unit. It's 1 Newton per meter square. Joule is a derived unit. Watt is a derived unit. Degree Celsius is a derived unit, right? So he was asking about the Fahrenheit. Fahrenheit would be a derived unit in USCS system. Okay. Then you also have the prefixes, and I'm sure most of you have been using prefixes without maybe paying attention as to when you should be using the prefixes, right? So if you want to write, let's say, I don't know, tera, right? You have terabytes of hard drives these days. What is that tera? 10 power 12, giga is 10 power 9, mega is 10 power 6, kilo is 10 power 3, hecto is 10 power 2, and you've probably not seen hecto and deca that much, right? You have 10 power minus 1 as deci, centi, milli, micro, nano, pico, right? So the whole prefix that you have probably seen in other places as well. But that begs the question, fine, we know the prefixes, but what are the rules? How do we really write those units? When should we use the prefixes? Okay? So once you know these rules, you will be able to rewrite the summary of that question that I presented to you, right? And you will be able to see what are the things that are wrong with it. So these are rules. Number 1, with the exception of Kelvin, unit names after individuals are not capitalized when written in full. Okay? So if you want to write joule in full, you're not going to make this J to be uppercase. Now you may say, hey, is that really that important? Yes. This is part of your communications. As an engineer, you need to be able to communicate properly. Okay? If you don't communicate properly, bad things happen. How many of you have heard about the instance where Mars Climate Orbiter was lost because the impulse was not reported in correct units? You've heard about that, right? So the impulse was not reported. The Mars Climate Orbiter was supposed to go into the climate of the Mars, but it actually got burned or crashed. We don't know what really happened to it. It was lost. NASA gave up because there were multiple teams working on the mission control, and the impulse, which has a unit of force times time, was reported as a number without providing the unit. And the guys who received the number assumed that it was in USCS system while it was actually in SI system. So they didn't really report the unit. It was assumed to be in the USCS system. And for the forces, there is a factor of 4.45 for the force that is used to do conversion from SI to USCS system for the forces. Okay? And it was that factor that was responsible for its loss. See, a very stupid and trivial mistake on the unit costed billions of dollars to the country. Right? So, it's a classic example of why you should write your units and why you should write them properly, because it's part of the communication. And if you don't communicate properly, then first of all, you don't come across as an intelligent engineer. Second, you could cause irreparable damages to the companies and organization you work for. So Joule, Pascal, Watt, all of these you can see written in lowercase, except when you are abbreviating them, then you can write them in uppercase, right? So capital N, capital W, and Pascal as PA. Don't use prefix for numerical values between 0.1 and 1,000. So if you have a value between 0.1 and 1,000, just write it like that. If you're more than 1,000, less than 0.1, use the prefix. So if you want to write, let's say, a 1 followed by 6 zeros, instead of writing that, write 1 megawatt, okay? Or anything larger than that. For fractional quantities, apply prefix to the numerator. So kilonewton per meter is 10 power 3 Newton per meter, which numerically would be same as Newton slash millimeter, because millimeter is 10 power minus 3. So it goes in the denominator, becomes 10 power 3. But instead of putting the prefixes to the numerator, always put the prefixes to the numerator. Don't write units in plural form while abbreviating. So when you're abbreviating, don't write 5, if you want to write 5 kilograms, don't write 5 kgs. Why? Because if you put S over there, people might think you're writing kilogram second. S might be construed as the short form for second. Dimension in SI units are written in lowercase, exception units named after individuals, which we have seen in point number 1. So when you write kilogram, you write 5 kg, where everything is lowercase, not capital K and small g, right? 2 meters, not 2 uppercase m meters. What about 5 kilograms? Is that okay? What about this? Can we write 5 kilograms like that? Yes, that's fine, right? Because you're not abbreviating. So since you're not abbreviating, you can write like this. So this is the same as something like this. So meters is fine. Don't use mathematical operations on unit names, right? So this was another thing that I think was done probably in that summary. So when you are actually writing everything using full words, don't use abbreviation. You're not using abbreviation, then don't use mathematical operations. So when you want to write joule per kilogram, write joule per kilogram, but if you're abbreviating, then you use a mathematical operation. So J/kg is okay, or J times kg power minus 1 is okay, although you don't see that also much. But don't do this, right? So here you're mixing mathematical operations, which is slash with the unit names written in full, or something like this. So that's also not allowed. Right? So it's very simple rules, but if we look at them, you memorize them, you practice them on a few problems, you'll have no issues whatsoever. And these are the kinds of things that are best learned at this level, because in future, you probably won't see this again. And this is sort of the good habits that if you form now in your early career, they'll stick with you. Okay, a few examples. So look at this. Anything wrong with this? 5 sec, 2 cc, 3 MPS.
Units should either be written in full or the symbol.
Or the symbol. So sec is not right. You can't say 5 sec. It should be either 5s or it should be seconds. 2 cc. cc is not an accepted acronym, accepted abbreviation. So it should be the 2 centimeter cube like that, or 2 cubic centimeters. 3 MPS. We don't know what you were trying to say. It's maybe meters per second. If it is meters per second, then you should say 3m/s if you're abbreviating it, or write in full, meters per second. You had a question? Or you were trying to answer?
Yeah,
okay. Okay. All right, maybe the next one. Length is equal to 75 centimeters. Anything wrong with this? Right, so we can't abbreviate it in the plural form. So if you have to write it like this, or you write 75 centimeters in full. The bar is 75 centimeter long. Anything wrong with that? I'm abbreviating the centimeter. There's nothing wrong with that. I can write that.
You don't need a period.
You don't need a period. You don't need a period after the cm, right? And a lot of times we do that, right? We put a period just like that because periods come for free. You can put them anywhere you want. Yeah. So no periods, right? So you say either the length of the bar is 75 centimeter, you just rephrase it, or you say the bar is 75 centimeter long. I think the first one is better phrase-wise. What's wrong with any of these? Mixing mathematical operations on the full name, right? That's what's wrong with these. So if you want to write this, either write that, or any of these things, that would be okay, right? What's wrong with this? 5 newtons or 5 ns? Should be lowercase, right? It should be lowercase, or you can, if you want to write it in uppercase, you basically write it in full. There is a technique called technique of dimensional verification that can be employed to check the dimensional consistency of equations and formulas. Now, that's one advantage of dimensional verification technique. The other advantage is that without knowing the physics of a problem, sometimes you can actually compute the rough expression for a quantity. And I'll show you how that is done, right? So let's first do the simple part, which is if somebody gives you an equation or a formula, you don't know anything about the physics of the problem, okay? But you do want to see if the formula is dimensionally consistent, right? So what does it mean for a formula to be dimensionally consistent? It means that if you have a left-hand side and if you have a right-hand side, then the dimension of the left-hand side quantity should be same as the dimension of the right-hand side quantity, right? Now, if you look at the quantities that are given to you in the formula and you write them in terms of base dimensions, fundamental dimensions, they should match across the equal to sign, right? So let's do that. So this is your famous formula, right? E equal to mc squared, okay? And what we want to do is we want to see if it is dimensionally consistent. So let's just start with right-hand side, okay? So we want to write the dimension of the right-hand side, right? Now pay attention over here because I've seen students making the mistake of writing things in terms of units. Don't do that. When I say use the dimensional verification technique to find an expression for something or to verify if the formula is correct or not, you have to write everything in terms of dimensions, not pick a unit system because unit system is relative. So what is the dimension of mass? M, right? So we write that as uppercase M. What is C? Is the speed of light, right? The speed of light is speed. What is what are the dimensions of speed? It's length over time because we know that average speed is defined as distance traveled over time. So distance traveled is length and over time is t. So that's L over t, that's the speed, but it is the square of it. So we have to do square, right? So what do we get? The right hand side is m times L squared times t power minus 2. When you bring t squared in the numerator, it becomes t power minus 2, right? Now, the quantity on the left-hand side should have the same dimension. If it doesn't have the same dimension, without knowing the physics of the problem, you can reject the formula. You can say, forget it. This is nonsense, right? Okay, so what is on the left-hand side? What is E? E is energy, right? Now, energies are different types. We'll see that. You know, we have mechanical energy. In mechanical energy, we have kinetic energy. We have potential energy. Then you have potential energy due to different kinds of forces. Potential energy due to gravity. Potential energy due to spring forces. Potential energy due to gravitational attraction. There are different kinds of energies out there. But they all have the same dimension. So as long as you can remember one formula for any energy, that's sufficient. So which formula for any energy do you remember? Force times distance, that's same as energy, right? Work done is force times distance, same as energy. Anything else? Any other formula? Half of mv squared, which is what? Kinetic energy, right? When something is moving, has a mass m, has a velocity v, its kinetic energy is half mv squared. You can pick any formula that you remember for energy, okay? So let's say we pick half mv squared as she said, right? So half mv squared. Now remember, half is a number, doesn't have any dimension, so we can neglect that. So mass is m, and v squared is, again, L over T whole squared, right? So you can clearly see that both of them have the same dimension. And that's a very simple verification. So you try to write every quantity in terms of base dimension, fundamental dimensions, and make sure that everything matches across the equality sign. If they don't, it's dimensionally inconsistent. So I may give you a question saying that here is a formula, tell me is it dimensionally consistent? Okay? All right, so that's a very simple way of using dimensional verification technique. The other is you can try to find a rough expression for a physical quantity in terms of some other physical quantity. So for example, the second one is assume a dependence of g, which is the gravitational acceleration, the length and temperature of the environment on the frequency of a pendulum, and find a dimensionally consistent form of the equation for the frequency. So, you know, if you have a pendulum of length L and of mass m, let's say, and over here the temperature is given as theta, and maybe and gravitational acceleration is g, because depending on where you're doing this experiment, gravitational acceleration could change, right? So you have all these quantities, and you know that, you know, you can compute the frequency of the pendulum. I'm pretty sure in your high school physics classes you have probably done this as an experiment. You hang a pendulum, you know, you just take it to the one side, release it, you start a stop clock, you count the number of oscillations, and you see how much time has elapsed in the oscillation, and from that you can compute the frequency, right? And you repeat that experiment a few times to get rid of any statistical error, right? So let's say we're not doing that experiment. We have some idea that the frequency depends on the gravitational acceleration, depends on the length, maybe even the mass, and the temperature, okay? And we're trying to find out what that form is, what that dimensionally consistent form is. Now remember, we're not really solving the physics of the problem. This is not a physics problem we are solving, because dimensional verification technique will not give you the exact formula, but it will give you the general form. So like, you might find out that f is directly proportional to L, okay, hypothetically speaking, which means that if you increase the length by twice, the frequency becomes double. So we are looking for that general expression, but it is not going to be an exact expression. So how do we solve a problem like this? It's very simple. We're looking for the formula for a frequency, and we are already given that it is dependent on the gravitational acceleration, the length, and the temperature, right? But we don't know whether f is equal to g, or is it g squared, is it g cubed, or is it 1 over g, or square root of g? We don't know that, right? So let's say we have these unknown exponents for each of these quantities. So it's g to the power a, L to the power b, t to the power c, right? And we don't know what a is, we don't know what b is, we don't know what c is, and that's something we need to find out. So if a is 1, if we can compute a to be 1, then we know f is proportional to g. If we find b to be 2, then we know f is proportional to L squared, right? If we find c to be 0, then t to the power 0 would be 1. That means f is not dependent on the temperature. So we're looking for the values of a, b, and c. So how do we find it? It's really very simple. So all we have to do is we have to write the dimensions of each quantity. Okay, so let's do that. What are the dimensions of gravitational acceleration? This acceleration? L times t to the power negative 2. Why? Because acceleration is rate of change of velocity. Velocity is L over 2. So L over t would become L over t squared. So that's L times t to the power minus 2. So we have L over T square to the power A, right? Now notice that we have assumed the exponents, which we don't know what they are, right? If you don't write the exponent, then you're essentially assuming that exponents are equal to 1. If you simply write f equal to g, then you're saying a is 1, which you don't know. So for every quantity that you write in on the right hand side, make sure they have some exponent. If you have 4 quantities, you'll have 4 exponents, okay? L, of course, is a base dimension, so that's L to the power b. Theta is also a base dimension, so that's T to the power c, right? Because we can't write L and theta any further. So let's collect all the like terms. So we have L to the power a and L to the power b, so that becomes L to the power a plus b. We have T to the power minus 2a, and we have T to the power c. Right? No questions about this? So we have L to the power a times L to the power b, which is L to the power a plus b. So this is all in terms of base dimensions now. There's nothing more we can do, right? This is reduced to the lowest possible level. Let's look at the left-hand side quantity. What is the quantity on the left-hand side? It's frequency. What is frequency? It's number of oscillations over a unit time, right? So what is the dimension of frequency? T to the power minus 1, or 1 over t. So the dimension of the left-hand side quantity is T to the power minus 1, right? Now, if this formula is dimensionally consistent, then the right-hand side quantity should also have the dimensions as T to the power minus 1, right? So we need to compare these exponents on the right-hand side with the left-hand side. Since we don't have any m here, so we can write this as m to the power 0, right? Why do I need to do this? Because, well, maybe I will have m on the right-hand side. If I don't have m, then I don't need to worry about it. We have L over here. Since there is no L over here, so I can write that as L to the power 0. There's no theta on the left-hand side, so I can write T to the power 0, right? Now I have basically all of these base dimensions on both sides. So if both of them are supposed to match, then a plus b should be equal to 0. So if you compare this with this, we get a plus b equal to 0. If you compare minus 2a with the power of t, it's minus 1, so we get minus 2a equal to minus 1. And that right away gives you a equal to 1 over 2. Right? And if you substitute a equal to 1 over 2 in here, that gives you b as minus 1 over 2. And what is c? C is 0, because there is no theta term on the left-hand side. So we found all the exponents. That's what we're looking for, a, b, and c. So if you substitute these values of a, b, and c in your original formula, which is this, what do we get? We get f equal to g to the power 1/2, L to the power minus 1/2, and theta power 0, which is 1. So what we get is square root of g over L. Right? So if you remember the frequency of a pendulum from your high school physics classes, what was it? What is the exact formula? So you have factor of 2 pi, right? So exact formula is f equal to 1 over 2 pi square root of g over L, right? You didn't get that 2 pi, sure enough, because you're not really solving the physics over here, right? So you didn't get that 2 pi, but you at least got the dependence on some of the input variables. So what it is telling you is that f is proportional to square root of g, and is inversely proportional to square root of L. So if you increase the length of the pendulum to, let's say, 4 times, then your frequency would become, if you increase the length to 4 times, your frequency would become, new frequency would be half of the original frequency, right? If you did this experiment on another planet where the gravitational acceleration was maybe, I don't know, 16 times of gravitational acceleration of Earth, frequency would become 4 times. That's it. So you're essentially getting a general dependence of some of the input variables, but you're not getting the whole physics. So you can't use the formula that you obtained from dimensional verification technique and use that, right? Because you don't have that factor of 2 pi. 2 pi is dimensionless, so you'll never get it, right? Okay, so that's the general technique. Another example. This is the example from your textbook 3.6. Okay, so this is a drill bit, right? A drill bit that's supposed to create holes in parts, right? So when you drill a part, and if the part is moving, then that part can actually exert a transverse direction force. So transposition force is a force that's perpendicular to the drill bit, right? So if, let's say, you apply this force F, because the part that you're trying to drill hole through is moving in direction perpendicular to the length of the drill, then essentially it deforms the drill bit a little bit, right? So if the material it's made of is very soft, then it could deform more. If it's very rigid, it's thicker, then it's not going to deform. But to some extent, all materials will deform, right? And that deformation may be very small, but there is some deformation. So this is known as a cantilever, right? Because it is being held at one point, and you're applying this force. So you'll see this cantilever beam model a lot in your studies over here, okay? So now the question is, if I apply this transposition force on the drill bit, knowing the length of this, knowing the diameter of the drill bit, knowing something about the material property of this drill bit, can I compute what the deformation would be? And when you take mechanics of solid or strength of materials class, you will learn that there is a formula that gives you that deformation. So delta x, which is the deformation at the tip, because the deformation is changing along the length, deformation is given by 64 times FL cube over 3 pi e d to the power 4. Okay? So let's look at each of those terms. In the numerator, you have factor of 64, which is dimensionless. You have F, which is the force applied. So more the force, more the deformation, makes sense. L cube. So deformation is dependent on cube of the length. So more the length, more the deformation, but it's actually not directly proportional. It's L cube. So if you increase the length by twice, the deflection would be 8 times, right? Because it'll be 2 cube. In the denominator, you have factors that reduce the deflection. And what you have is the E. E is the elasticity modulus, which we'll talk about in maybe 2 classes from now. And elasticity modulus is a measure of the material property, how tough it is, what kind of material it's made from. So elasticity modulus for steel is different from aluminum, from plastic, and so on. And D is the drill diameter. And of course, you know that if the drill bit is made of thicker, then of course it's going to deform less, right? And that is D to the power 4, okay? So the question is, given this formula, can you say something about the dimensional consistency of this formula? Is it dimensionally consistent, right? That's the question. So it's easy to find. All we have to do is write all of these things over here on the right-hand side in terms of base dimension, and write the quantity on the left-hand side in terms of base dimension. If they match, it's dimensionally consistent, right? So let's do that. So F, let me write dimensions of each of these quantities separately first. So what are the dimensions of force? We know force is mass times acceleration, so that's m times. Acceleration is L times t power minus 2. L, of course, is L cube, so L is L, so I don't need to worry about that. E, okay, E, which is the denominator, is elasticity modulus, and you're given the definition as force over length square, so that is the force divided by L square, and then you have the D, which is L, right? So let's substitute all this in. So we have 64 times FL cube over 3 pi E d to the power 4, and we don't need to worry about 64 and 3 pi, they are dimensionless quantity. F is mLt power minus 2. L cube is L cube. E is mLt power minus 2 over L square, that's E, and then we have d to the power 4, so we have L to the power 4, right? Okay, so all of this cancels. This L square will cancel this to make it L square, so you will have L cube over L square as simply L, right? And on the left-hand side, you have delta x, which is the dimensionless length too. Problem solved. Is dimensionally consistent, right? And you will see this technique being used in your fluid mechanics class, where you will come up with what are known as dimensionless numbers, which characterize the ratio of different kinds of forces. Anybody here in any fluid mechanics class or has taken a fluid mechanics class? So you're probably aware of Reynolds number, Prandtl number, Lucent number, and those are basically the ratio, and they're dimensionless numbers that are obtained via the dimensional verification technique. So you will see great use of this, especially in your fluid mechanics classes. Okay, but at least, you can impress your friends. If they try to come up with a formula, you can tell them, hey, what you're telling me is useless because it's not dimensionally consistent. Okay, ingenious idea of discussion in parties, right? Use the dimensional verification. So we've been talking about problem solving, right? And we're talking about dimensions, we're talking about the units, and we already seen a good use of dimensional verification technique. And a third attribute of problem solving is looking at the numbers that you may have computed in a problem or you may have measured experimentally and asking the questions about the quality of the numbers that are reported, right? And here is an example. So these are the numbers for Bolt's world record in 100-meter sprint. He traveled distance of 100 meters in 9.58 seconds, as is being shown on this display, digital board, right? Somebody said, hey, let's find out what is the average speed because I want to compare the speed of this with the speed of my car, right? Okay, so you plug in all these numbers in your calculator, and your calculator reports all these numbers in meters per second, which you can convert into miles per hour, and you get to this number 23.34968684 miles per hour, right? Depending on your calculator, you may get more digits or less digits, right? Okay, so you get this, and do you report this number just like that? Of course not. You know that there is something wrong with this answer. What is wrong is that you have the distance of 100 meters. The time is reported as 9.58 seconds. You have only 2 digits after the decimal, but somehow your final answer seems to indicate that the answer is much more precise than any of the input quantities, right? You've heard a saying, garbage in, garbage out, right? So in this case, it's not exactly garbage what you have in here, but it is limited in quality. The number that are being used in the input are limited in quality, right? What is that limit? Limit is that you have only 2 digits after decimal, and there's 1 digit before the decimal. So altogether, you have only 3 digits in both the numbers for the distance and time. And somehow your answer seems to be much more precise than any of the input quantities. That can happen. That's wrong, right? Okay, another example. If you're trying to compute, let's say, the force exerted on an object of mass 2.5 kilogram and acceleration is 1.236 meters per second square, you can compute that force using the Newton's second law, multiply the two numbers, and you get your answer is 3.09 Newton. And that's the number you get from the calculator. So if you multiply those, you plug in your calculator, you'll get 3.09 Newton, right? So at least the good thing with this is that it is not a very long number like you see over here, but it is still some number. The question is it meaningful to report that answer just because your calculator is spitting it out? Anything wrong with that? Sure, we don't know, right? We need to investigate that. We need to have some sort of logic behind reporting the numbers, right? So these are the questions. Okay. So before we talk about how we can resolve those problems, the problems that we saw in the previous slide, let's talk about different kinds of numbers, right? There are 2 kinds of numbers out there. There are exact numbers, right? Number of students in this class, that's exact, right? We can't have, if we have 250 students, that's 250 students. We can't say we have 249.56 students. Not going to happen, right? Number of hands, number of legs. So those are all exact numbers. And somehow those numbers have maybe infinite precision, a different kind of quality about them, right? There is a sense of absoluteness about those numbers. And that's why they're called exact numbers, right? You also have unit conversion factors in the formulas like 1 meter equal to 100 centimeter. That number of 100 is an exact number. Okay? Within the same unit system, the conversion factors that you use are exact numbers. But if you go from one unit system to another, like USCS to SI, the unit conversion factors you use are not exact numbers. Okay, so this is the example. So if you go from 1 kilogram to pound mass, and it's 2.2046, 2.2046 is not an exact number because you went from one unit system to another. Okay, and that's the general convention. So in exact numbers, we talked about that. Any value that you measure using some sort of measuring scale or you compute are in general in exact numbers. Okay, so they don't have that, the kind of quality like exact numbers have. Okay, so we're talking about the quality of the number. How do we measure the quality of a number? Whether it is computed or whether it is measured, right? And there are 2 attributes for the quality of a number. One is the preciseness, how precise that number is, and the other is the accuracy. Now, a lot of times in our day-to-day conversation, we actually mix these 2 terms, right? When somebody says, hey, my height is 5 feet 7.67 inches, am I being accurate or am I being precise? Precise? I'm being precise? Oh, exactly. So accuracy will really depend on how tall actually I am. I'm saying I'm 5.678 inches. Definitely, I'm giving a lot of digits after the decimal, so it makes it look like as if I'm being very, very precise, but it may still not be accurate, right? I may be lying to you. I'm just giving you a large number to make it look like as if, there is a great quality in that number, but it may not be accurate, right? So accuracy and precisions are not to be mixed with. There are two different factors that describe the quality of a number, right? So what accuracy measures is the truthfulness. What is the actual height, right? What is the actual mass? What is the actual number? And how do you know what is the actual height? How do you know what is the actual number? There has to be some sort of known, trustworthy scale or a reference that you have to use to know what is the actual number. There's no other way. Okay, so there might be a mass of 1 kilogram kept in some lab in Paris, right? The 1 kilogram is still defined that way. It's a known mass that is kept in some lab in I don't know, some part of Europe, somewhere. Yeah, right, somewhere. I remember that in high school, but I don't remember that now. So it's somewhere there, and that's your reference. So if you really want to see if something if something has mass of 1 kilogram or not, if you want to compare the truthfulness of the mass, you have to compare it with that thing. Okay? So that's truthfulness. That's veracity. That's the accuracy. And accuracy is something that is not easy to verify. Okay? You just have to trust your instruments that are given to you and say, hey, I trust this instrument. It's not something that is rigged or has maybe deformed, right? For example, if you take your, 6-inch ruler, okay? You take your 6-inch ruler made of maybe wood, okay? Wood has very low thermal expansion. But if it is made of from another material that has a large thermal expansion and you use it in a hot area, it could expand, right? So your inch ruler has now become incorrect. Right? No matter how accurate it is, no matter how precise it is, how many gradations are made on it, now it has deformed, it has expanded. So anything you measure from it is going to be inaccurate. It may be very precise, but it is going to be very inaccurate. Right? So precision is something that depends on the measuring instruments, the instruments that you have, or the computer or the calculator that you have, which you are using to compute numbers. Okay? So precision is easy to see because it directly relates to your computation, your computing tools, and your measuring tools, right? So another example of precision is where you can reproduce something again and again. So if there is less deviation in measurements, you're being very precise. It may still be inaccurate, right? So this is the example of the bullseye, right? So if you're around the bullseye and you have a lot of dispersion, so you have very high accuracy because you're close to the bullseye, but you have very low precision because you're shooting here, now you're shooting here, now you're shooting here, right? On the other hand, you could be very precise, but you could be completely off the target. All of your data points are clustered together, so you have very high reproducibility, very high precision, but very low accuracy, right? So if, let's say, there is a calibration problem and you're doing experiments correctly, this could happen. So you have precision, but you don't have accuracy. So now the question is, how can we measure the preciseness property of a number, right? And that's where sig digits can come in, right? So you may have already read about sig digits before, or you may have been taught about this in your high school classes, okay? But the idea is that sig digits are important, and it's something that you need to take inside your brain and use it every day. Every time you look at numbers, you're doing any kind of computation with them, anytime you're measuring something, you need to have significant digits in your mind. Make it part of your habit, okay? Because this stuff will not be taught to you again in our department. Nobody will talk about sig digits, but everybody will expect you to know. Nobody will talk about how to write the units. So if you don't learn it now, there will not be another time, okay? So what's a sig digit? Well, sig digit tells you something about the precision of a number, preciseness of a number, okay? So when you measure something, when you compute something, you can talk about the numbers that are being reported, which you can trust. Now, when you write numbers, there is always an estimated digit in there. The last digit is usually the estimated one. So where does that come from? And how do we really count how many sig digits we should report and all that? So for that, let's look at a few examples. So let's say we're trying to measure the volume of some fluid inside a beaker, okay? And we have these gradations. Now the gradations are your tool for measuring the volume, right? You can't be really more precise than the gradations. So if you look at these gradations, you can see the level is somewhere over here. And where is this level? This is between 40 and 50, right? It's between 40 and 50. So is it 46? Is it 47? What would you say? 46, 47? Something like that, right? So you could say it's 47, but your last digit is an estimated one, because it could be really 46, it could be 47, it could be 48. You have plus minus 1 ml as the tolerance, because your last digit is estimated one, right? So this is a unit place, so it becomes 47 plus minus 1 ml, right? And you cannot really report more than that, okay? Then you have, let's say, something a little bit more accurate, graduated cylinder, right? Now, graduated cylinder has a meniscus, something like this. It is not like a flat section of fluid. So now you're looking at this, and you're looking at the lowest point of this meniscus, and you see that it's between 36 and 37, right? So is it 36.5, 36.6? You could definitely say it's 36.5 or 36.6, but you know that your last digit is going to be estimated one, so it's okay to report it as 36.5, and it's plus minus 0.1. So if somebody says it's 36.6, that'll be okay too. Somebody says it's 36.4, that'll be fine as well, right? Because you're only looking at this level with your naked eyes and trying to estimate what that last digit would be. So it's an estimated one. Okay, let's look at a burette, right? And I'm sure you guys have used all of these things in your high school chemistry classes. So now burette is supposed to be even more accurate. So you have gradations which are finer, but it's in the reverse now. So here is 20, here is 21. So you have 20.1, 20.2, 20.3, and 20.4. So it's between 20.3 and 20.4. Where could it be? It could be maybe 23.37, 38, something like that. Doesn't matter. You just write 20.38, let's say. And we know the last digit is estimated one, and this is the 0.01 place, 10 power minus 2 place. So the tolerance is plus minus 0.01 ml. Right? So depending on your measuring instrument, you can report different number of digits. But you always know that your last digit is an estimated one. Okay? That's where you could have some uncertainty. But the other digits are fine. There's no problem with them. So that gives the idea that we can report numbers which could be more precise, less precise, and that precision could be measured by a tool called significant digits. In short, we call them sig digits. Okay? So now there are rules for counting how many sig digits you really have in numbers. Okay? And these are the rules. So number one rule is that non-zero digits are always significant. Now, I'm sure some of you have seen this before in your high school classes, but so let this be the refresher, and if there is something that you don't remember, maybe this will help with that. So non-zero digits are always significant, okay? So 22 has 2 sig digits, 22.3 has 3 sig digits, all right? Now, the situation with zeros is a little bit more involved. It's not that straightforward. So zeros could be before, could be after, could be in between. So let's look at the case when the zeros are placed before other digits that are not significant. So you have 0.046 and clearly 46, these two are sig digits, but the 0 placed before them are not significant. So this 0 before the decimal, this 0 after the decimal, but all of these zeros are before these sig digits are not significant. Okay, so this has only 2 sig digits. Zeros that are placed in between other digits are okay, they're significant. So this is going to have 4 sig digits because both the zeros are significant over here. Zeros placed after other digits but behind the decimal points are significant. So if you have zeros after a decimal point, they are significant. Now this is important. So if you have never seen the concept of sig digits before, this may be a little bit strange to you, because 7.90 has 3 sig digits. But if you simply write 7.9, which is essentially the same number as 7.90, numerically speaking, that has only 2 sig digits. Okay? So if I say 7.90, the last digit is an estimated one, which means the actual answer is somewhere between 7.89 to 7.91, right? Because the tolerance is plus minus 0.01. But if I say the number is 7.9, then 9 is the estimated digit. That means the actual number would be 7.828, right? Because it's plus minus 0.1 then. So that changes the quality of the number completely. Even though numerical, the both numbers are the same, but where you place the zeros can make a lot of difference. When you say 7.90, then you're saying that I'm more precise than if I was reporting 7.9, because maybe my measuring tool was a little bit more precise, right? So this is a reflection of the measuring tool as well, or the quality of your computation, or the computational tool that you're using. So then the question is, okay, all right, so 7.90 has 3 sig digits, the 7.9 is the same number, so what should we really do, okay? So the rule that we use is that you use the scientific notation, okay? You use the scientific notation, so you may have the same number, but you can use the scientific notation to get rid of this 0 problem. So if you write 8.200 into 10 to the power 3, which is same as 8.20 into 10 to the power 3, which is same as 8.2 into 10 to the power 3, numerically, they all have, the numerical they're all same, but sig digit wise, they're all different. This has 4, this has 3, this has 2 sig digits. Okay? What about these numbers? What about 820? 2 digits. So this 0, how, do we know if it is significant or not? We don't know. It's ambiguous. So never write numbers like this, because when you write 820, we don't know whether that last 0 is significant or not. Okay? So if you have 3 sig digits, then you should write 820 point. That's it, just a dot. Or the other option would be to write 8.20 into 10 to the power 2. Then you know that has 3 sig digits. Right? 8200, again, we don't know if these 2 zeros are significant or not. We do know that 8 and 2, those 2 numbers are significant, but the last 2 zeros, we don't know. It's ambiguous. So whenever you're in a situation like this, if you use the scientific notation, you won't run into these ambiguity problems. You had a question? Okay, good. All right. So the rules are fairly simple. You just look at them, read the slide a couple of times, and you'll get it. Okay. And now I have a few examples so you can see it. All right. So now we know how to count the sig digits, right? That's great. How do you use them in calculations? Because you'll be doing a lot of calculations. You'll be given input quantities. I'll be asking for output. So when you multiply things, when you add things, when you subtract things, you use the sine, cosine formula on them. What should be your final answer reported as? How many sig digits your final answer should have? How many sig digits your intermediate calculations should have, right? That's the question. So we will divide this into 2 halves. One is where you're doing multiplication, division, using functions on the numbers, sine, cosine, logarithmic, exponential, and so on, right? When you have situations like those, you look at your expression, you look at your numbers. As long as the expression involves just multiplication and division and using the function, the input quantity that has least number of sig digits decides how many sig digits you will have in the final answer. Okay? So the final answer should have same number of sig digits as the input quantity that has the least number of sig digits. So if you have 5 input quantities that you're multiplying and dividing and taking sine and cosine off, then the one that has the least sig digits are the ones that should be used for the final answer. Okay? So example, now this is the example that we looked before. So you're trying to compute the force on an object of mass 2.5 kilogram, acceleration is 1.236. Those are the 2 input quantities that you're multiplying. This has 2 sig digits, this has 4. Your final answer should be reported in 2 sig digits, right? So if you compute this, you put the numbers in calculator, you get answer as 3.09, which has 3 sig digits. So you need to round it to 2. And if you round 3.09, you basically get 3.1. So the question is now, how do we do rounding, right? That's coming. So the question of rounding will be answered pretty soon. But this has 2 sig digits. If you're doing addition and subtraction, the rule is slightly different. You don't count sig digits. You look at the input quantities, and you look at the input quantity that has least number of digits after the decimal, and you report those many digits after the decimal in your final answer. That's the rule for addition and subtraction. Okay, so it's not decided by the number of sig digits. Sometimes sig digits may be same as if you use the sig digit rule, the answer may come out to be same, but the real rule is that you just look at the decimal places after the decimal for addition and subtraction. Okay, so if you want to add these 3 numbers, these are these are numbers which are for energy, let's say, because you have joule over here. So you have 2 digits after decimal here, 1 and 4 over here. So your final answer should have only 1 digit after the decimal. So you plug in these numbers, you add them in your calculator, and you may get a number which has maybe 3 or 4 digits after the decimal. You have to round it so that you have only 1 digit after the decimal. Okay. Now the question is, what do you do with your intermediate calculation? So you may have maybe 10 things that you have to compute before you report your final answer. General rule is that for your intermediate calculation, you try to retain as many digits as you can. Okay, so if you're doing all the calculations in your calculator, you don't need to worry about it, right? Because your calculator is storing a large number of digits after decimal, or has very large number of sig digits. It's only when you report your final answer, you look at your input quantities, and you report the right number of sig digits based on the rules we discussed. Okay, if you're writing intermediate calculations on a piece of paper, maybe this is exam or homework, and you want to show what your intermediate answers are, you report up to 4 digits after decimal. Okay, 4 digits after decimal. So that means you'll at least have 4 significant digits, right? And then your final answer should follow the rules that we just talked about. Okay, so then the question is, what are the rules for rounding off, right? And a lot of students make mistakes with that. So this is where you should pay attention. So first rule is, if the digit to be dropped is greater than 5, the last retained digit is increased by 1. So for example, 12.6 is rounded to 13 for 2 sig digits. So if somebody says, hey, this is the number, rounded to 2 digits, so then 6 is more than 5, and this is the one you're dropping, so it becomes 13. If the digit to be dropped is less than 5, the last remaining digit is left as it is. So if you have 12.4 and you want to get rid of 4, because you have to round it to 2 sig digits, 4 is less than 5, so the answer is 12. Okay. If the digit to be dropped is 5, if any digit following is not 0, the last remaining digit is increased by 1. So if you have 12.51 and you have to round it to 2 digits because you have to drop the 5, 1 is not 0, so this becomes 13. 12.51 becomes 13. If the digit to be dropped is 5 and is followed only by zeros or nothing after that, the last remaining digit is increased by 1 if it is odd, but left as it is if it is even. And this rule is pretty arbitrary because you want to sort of even out the playing field, right? You don't want to bias the rounding for odd number versus even numbers. So for example, if you have 11.5, after 5 there is nothing and you have to round it to 2 digits, you have 5. So you look at the number before the 5, 1, which is odd. So this becomes 12. And if you have 12.5, you have 5, nothing after that. You have 2 here, which is even. This is left as 12. So 11.5 is rounded to 12, but 12.5 is rounded to 12. Okay? This is just an arbitrary rule. Don't round off progressively. So I've seen students making that mistake too. Okay? So if you have, let's say, a 5 sig digit number like this, and you have to round it to only 3 sig digits, then don't do progressive rounding. Right? So what is progressive rounding? You reduce from 5 to 4, then from 4 to 3. Okay? So if you do that, this is what you will get. So if you round 827.48 to 3 sig digits in one shot, you look at the number that you're dropping. 4 is being dropped, and since 4 is less than 5, the answer is 827. But if you do progressive rounding, see what happens. You have 827.48, you drop 8. Before 8 is more than 5, so this becomes 827.5. And then again, when you round it, because this is odd, this becomes 828. So the answer is different if you do rounding in one shot. So don't do progressive rounding. Okay, that's something that I've seen students doing, maybe because that's how they learned it before. Exact conversion factors have infinite sig digits. So exact numbers, if you have exact numbers in a formula, in an expression, if you have exact conversion factors, like 1 meter equal to 100 centimeter, 100 is an exact number. Exact numbers have infinite precision. So they have infinite sig digits. Okay, so a few examples. So you want to round this to 3 significant figures. You have 2.3467, and we have to drop the 6 over here. 6 is more than 5, so this becomes 2.35, right? So I'm just going to leave this. You guys can do this when you get home, and I have the answers over here, right? And I will leave this quiz for you guys to work on too, okay? And I'll have the answer in the slides, so you'll be able to look at them. So I don't want to spend too much time with the sig digit stuff. Okay, so problem solving. Now, this is a problem solving chapter, right? And most of you probably have been using some sort of problem solving technique in the past, right? It's very likely you're in the mechanical engineering or civil engineering program, or one of the other engineering programs. You couldn't be in the engineering program unless you learn how to do problems, right? And you probably have some method. And in your high school classes, your teachers may have taught you how to do the problem solving. So what I'm going to tell you over here is a very simple approach, okay? There's nothing, really new in there. It is something that you may have been following, or maybe a variation of it, right? But this will be a good time to concretize that idea, that you need to follow a systematic approach to solving the problem. And the reason is that you want to use, especially for the complex problem, you want to have a method for solving the problem. You want to use the divide and conquer approach. What is divide and conquer approach? You look at the problem, you try to divide into multiple pieces, okay? So that you are not really, inundated with the information given to you, and you're trying to simultaneously think how to solve the problem looking at the information. I'm going to give you an approach which we call given, find, how, solve approach, okay? It's a very simple approach where you basically just have your solution presented in 4 sections. Given, find, how, and solve, right? As the name implies, given is you just look at the input information, you write that down. Find is you write down what is it that the question is asking for. How is where you write the governing equations and the formulas. And solve is finally the solution. Okay, so everything that we talked about, about the competition, about significant digits, about the rounding, how to write the units, will appear into this last section, solve, right? Okay, so what's in the given? The given is you read the problem carefully, okay, very carefully. Everything that is given to you in the problem, you write that down. Simple example. A boy is traveling at a constant of 10 meters per second along east. Find the distance traveled after 10 seconds, right? And your first instinct may be, hey, this is such a simple problem. I can just go ahead and write the formula and solve it. And that may work for simple problems. But when you get to the complex problem, and you will see, when you take engineering dynamics, which is probably one of the toughest class you will take in our department, at least when you come in, it feels very tough. Although it's a very analytical, a very simple class, if you pay attention. And you will see the problems become very complex. Sometimes they run into like half pages. If you're reading a half-page problem, you need to write down, jot down everything that is given to you in the problem. If you don't do that, you will be hunting for that information again and again by reading the problem. Okay, so first thing you need to do is write what is given to you. In this problem, you're given the constant speed. So write that. Velocity is 10 meters per second along east, right? And you can use symbol at this point. So that's fine. So you can say v equal to 10 meters per second along east. Time is 10 seconds, and acceleration that you're deducing from the constant speed, because you need to use this information somewhere, right? Constant speed. So either you write constant in parentheses next to 10 meters per second, or you can directly say, I know velocity is constant, so the acceleration has to be 0. Okay, so you deduce some input information, and you wrote the acceleration as well. That's the given part. What is to be asked? What is being asked? Find S, the distance, right? So again, you use the symbol S, because you will use these symbols in your governing equations, and finally when you solve it, right? Again, you're not just trying to solve it yet. Given, find. Then how do you do it, right? So this is where you need to know what the physics of the problem is. What are the governing equations? So we're talking about relating velocity, the time with the distance. We know there is a simple formula for that, which is that if something is traveling along a straight line, then speed can be given as the distance traveled over time, right? So you write that formula. So in this case, you have one equation, you have one unknown. You know v, you know time, you only need to find out what S is. But you will see that sometimes you have more than one unknown. You have 2 unknowns. If you have 2 unknowns, you need 2 equations. If you have 3 unknowns, you need 3 equations, right? So you need to count how many unknowns you have and how many equations you need. In this case, 1 unknown, 1 equation would suffice, right? You got that, and then finally you go and solve it, right? So this is where you plug in the numbers. So you know the velocity, you know the time, you plug that in, and you get your answer as 100 meters. Assuming that this 0 is significant, you can see that we have 2 sig digits in each of the input numbers, so your final answer should be reported in 2 sig digits. So you can't simply write 100 meters, right? That would be wrong. And this is something you may be doing until now, but you have to stop doing it, right? You have to count the sig digits. So the next homework assignment will be on the problem solving. So every problem you solve, you'll have to take sig digits, unit, how to write units, all that into account, right? And you'll have to do the same thing going forward. So it's not like that homework 2 is about problem solving, so you just worry about sig digits and unit writing in that homework, and then you forget about the rest of your homework, okay? It's not going to work like that. We will pay attention to how you're writing the units and how many sig digits you're reporting. Another example. So we'll talk about the stresses and the strain in a few classes from now, okay? So stress is something that develops in an element, in a part, in any geometry, when forces are applied on it, okay? And very simply put, stress is defined as force over a given area, right? And you can clearly see that it's almost like pressure, the fluid pressure, right? Except that it's not for fluid, this is for solid materials. So if I take this in my hand and I really try to stretch it, apply some force, there's a cross-sectional area. That force divided by the cross-sectional area of this remote will define the stress on it, right? Okay. So the question is, calculate the stress in SI units, that's an MKS system, in a 0.5-inch diameter cable supporting a 1,000-pound mass truck engine. Okay, so you have a you have a 1,000-pound mass, well, this is half ton, this is 1,000-pound mass truck engine, and there is a cable. We're looking for the stress in this cable, okay? We're looking for the stress. So what is given to you? Let's write that. Given is force, 1,000-pound force, which is in Newton is 4,450 newtons. And remember, I would expect you guys to remember some of these conversion factors, okay? Not the esoteric ones, but the straightforward ones, like how do you go from pound force to Newton? How do you go from maybe foot to meters? Those kinds of unit conversion factors, I will expect you guys to remember. It's something that you have to do. Okay, you know, this is not a chemistry class where you have to remember a gazillion formulas, but you do need to remember a few very basic conversion factors. Okay, you won't be provided that in the exam, so you have to remember at least these kinds of factors. So how many feet you have in a mile, right? How many feet you have in a mile? Anybody? Right? So 5,800, so whatever it is, you need to remember that. Okay. All right. So we know the force, we know the diameter, which is 5.5 inches. We need to find the stress, sigma, and we are using sigma as a symbol in SI units. How? The formula is the stress is F over A. We know the F. Area is pi r square or pi d square over 4. So we can compute area. Let's solve for it. Area, plug in all the numbers. So this is 3.5 in inches. 1 inch is 2.54 into 10 power minus 2 meter, right? So because in 1 inch you have 2.54 centimeters, you get that. And then you write in, and this is again all in meters square. You write your sigma equal to F over A. F is in Newton. The area is in meters square. And you get your answer as 8.8 10 power 6 newtons per meter square. Why this much? Because you have in the diameter. Right? This is an inexact conversion factor because you're going from USCS system to SI system. So this has 4 sig digits. This has only 2. So your final answer should have only 2 sig digits. Right? Okay. So this is fairly simple. Again, like I said before, you may have seen some of this stuff before, but hopefully this was a good refresher.